Okay, we're going to start looking at some geometry problems using our vector skills. So we're going to start with our vector skills and then we're going to solve some simple geometry problems. When we're doing these problems, it's always a good idea to draw a diagram and think about our shape, what must be true about our shape. And the diagram and just having a think about what shape we're investigating will really help us solve these problems. So let's have a look at this first one. The points A, B, and C have position vectors 1, minus 4, 8, 4, 4, 7, and 10, 0, 30 relative to the origin O. Show that OA equals the magnitude of OA equals the magnitude of OB, and that the magnitude of AC equals the magnitude of BC. Hence, describe the quadrilateral OACB. Well, let's start with these magnitude questions. So OA will be, we'd find that using end minus start. Because it starts at the origin, OA will just be equivalent to that position of A. So it starts at 0, 0, 0, it ends at 1, minus 4, 8. So OA equals just 1, minus 4, 8. And the same is going to be true of OB. So OB is just going to be 4, 4, 7. Okay, so let's see those magnitudes. So the magnitude of OA, we take each component squared and we take the square root of that. So OA, magnitude of OA, so how long OA is going to be 1 squared plus minus 4 squared, that minus should be in the bracket there, plus 8 squared. So that's going to be 1 plus 16, 1 plus 16 plus 64. So that becomes 70, 80, 81. So this equals square root 81. And then I have magnitude of OB, which is square root 4 squared is 16, plus 16, plus 7 squared is 49. So hopefully that is also 81. So 16 plus 16 plus 49, 16 plus 16 plus 49 is in fact 81. So that is the square root of 81. So therefore we've shown that these two have the same magnitudes. And we're going to do the exact same thing again. So I'm going to find AC, let's just get the vector first. So AC, I'm going to use end minus start. So my end point is at C, which is 10, 0, 30. It begins at A, which is 1, minus 4, 8. So the vector is 10 minus 1 is 9, 0 minus 4 is 4, 30 minus 8 is 22. Okay, and then we can look at, let's make this slightly less chunky. So BC. We're not getting the magnitude yet, we're just looking at the magnitude. We're not getting the magnitude yet, we're just looking at the vector. We're going to use end minus start. So it finishes at point C, which is 10, 0, 30. It starts at the position B, which is 4, 4, 7. So the vector BC is going to be 10 minus 4, which is 6, 0 minus 4, which is minus 4, and then 30 minus 7, which is 23. Okay, so we're asked to show that these two magnitudes are the same. So we have AC, the magnitude of AC, or the length of AC, is going to be square root 9 squared plus 4 squared plus 22 squared. And the magnitude of BC over here is going to be 6 squared plus minus 4 squared. That negative will just go away when it's squared, plus 23 squared. So let's look at these and hope that they're the same. So for this first one, it's 9, 4, and 22. Square root 9 squared plus 4 squared plus 22 squared is square root 581. 581, and we're going to hope that this is the same over here. So it's 6 minus 4 and 23. So we have square root 6 squared plus minus 4 squared. We could just ignore that, plus 23 squared. No idea why I put that one in brackets. Root 581, square root 581. So these two are the same length. So describe this quadrilateral OACB. So if I draw my diagram, let's put it over here. So what we can see is I have these vectors. So I have OA and OB have the same magnitude. So I've drawn them in light blue here. Also, AC and BC have the same magnitude. So if these two sides have the same magnitude, this overall shape has to be a square. I can't really move C out of the way because then I've made OA longer than OB, so I can't move C up. I can't move C to the right. So it just has to be where it is. So it's a square. Okay, let's look at this one. The points A, B, C have the coordinates 215, 443, 275 respectively. Show that the triangle is an isosceles. Find the area. Find the point D so that it's a parallelogram. So let's do a diagram first. We're told that it's a triangle, so let's just start with something vaguely triangular. I'm not really too bothered whether these are in the right places in space. To show that it's an isosceles, what that will mean is two of the sides will have the same length. So what I'm going to do is I'm going to investigate the lengths of each of these sides. So this would be the magnitude of the vector AB, will be that length here. This would be the magnitude of the vector BC here. This length will be the magnitude of the vector AC. So what I'm going to do first is actually just find those vectors. So I'm going to say AB equals end minus start again. So that's going to be 443 minus 215, which is 2, 3 minus 2. So this length is going to be, so the magnitude of AB is going to be square root 4 plus 9 plus 4, which is square root 13 plus 4 is root 17. So that's root 17. And then we have BC. So we're going to do end minus start. So it ends on C, 275. Begins on B, 443. So that equals 2 minus 4 is minus 2. 7 minus 4 is minus 3. 5 minus 3 is 2. So the magnitude of BC is going to be 2 squared is 4, plus 3 squared is 9, plus 2 squared is 4. So again, that's, hey, look at that, happy days. So that's 13 plus 4 is square root 17. And there you go, we've already shown that it's a isosceles there because we have these two lengths which are the same, two sides which are the same length. And just for completion, let's find this last one. So I've got AC, end minus start. So end minus start, the end point is 275. It begins on 215. So this vector is 0, 6, 0. Well, we can already see that the length of AC there is going to be the square root of 6 squared, which is just 6. So that's going to be 6. So find the area of the triangle. Here is my triangle. Let me just, perhaps if we rub this out, it just becomes clearer. All we have here is an isosceles where we know the length of every single side. So not an extremely complicated question. Obviously, this diagram's not to scale, but we can basically just do half times base times height here, where we're splitting this up into two smaller triangles. So if I split this up into this triangle, this will have a length 3, this will have a side of root 17. This will be a right angled triangle. So what I can use is I can use some Pythagoras to find this final unknown side here. So I get this side, and when I know when I've got that final side, I can do half times base times height. Get this yellow length here. I'll give it a name. I'll call it Z, and I can find the area of this smaller right angled triangle. So let's actually do that. Let's I'll tell you what. Let's get some space. So let's go ahead and pull this down. And we'll I'm going to rewrite my triangle over here, this half of my triangle. So I have root 17, 3, this is 90 degrees. Let's label this up. So hypotenuse, B, C. So I know hypotenuse squared equals B squared plus C squared. So I know root 17 squared, which is just 17, equals 3 squared plus this b squared. So b squared equals 17 minus 3 times 3 is 9. So b equals square root 17 minus 9, which is root 8. So this is root 8. So the area of the triangle is going to be 1/2 times base times height, which will be 1/2 times by 3 times by square root 8. So that's the area of this 1/2 of this triangle, this green triangle. So my whole triangle area will be 2 times this. So I'll redraw this. So I've got this triangle, this whole triangle. We've just worked out this area to be 1/2 times 3 times 8. So obviously there'll be another one here. So my whole area of the whole triangle is going to be 2 times 1/2 times 3 times root 8. Okay. I think we'll just do this last one and then we'll move on. So the points A, B, C, D have the coordinates 7, 12, minus 1, 11, 2, minus 9, 14, minus 14, 3, and 8, 1, 15. Show that A, B, and C, D are parallel, and find the ratio A, B, C, D in its simplest form, hence describe this quadrilateral. Okay, so let's start with finding these vectors. So A, B, I'm going to do end minus start as per usual. So ends on B, so that's 11, 2, minus 9, begins on A, 7, 12, minus 1. So this vector is 4, minus 10, minus 1 is plus 1, so that's minus 8. So then we have CD, so ends on D, begins on C, so D is 8, 1, 15, C is 14, minus 14, and 3. So we have this vector CD is 8 minus 14 is going to be minus 6. 1 minus 14 is going to be plus 14, which is 15. And then I have 15 minus 3 is 12. Now I've got to prove that these two vectors are parallel. So are the two vectors 4 minus 10 minus 8 parallel to minus 6, 15, and 12? Now, if they're parallel, there should be some way of making one vector a multiple lambda of the other. So there should be some consistent lambda where I can multiply this second vector and reach this first vector. So it should be the case that I have a consistent lambda, if I look at i's, j's, and k's separately, where I can say 4 equals minus 6 lambda, minus 10 equals 15 lambda, and minus 8 equals 12 lambda. So I should have this 1 lambda for each of these same equations, and if I do, they are parallel. So 4 divided by minus 6, so lambda equals 4 divided by minus 6. 4 divided by negative 6 is negative 2/3, negative 2/3. So lambda again here will be minus 10 divided by 15. So minus 10 divided by 15, same value, which is looking really good, minus 2/3. And then minus 8 divided by 12, minus 8 divided by 12, same value, so that's fantastic. So lambda equals minus 2/3. So what I can say is that this first vector, 4 minus 10 minus 8, equals minus 2/3 times by this second vector, minus 6, 15, 12. Therefore, they are multiples of each other, multiples. Therefore, they are parallel. Okay, right. I'm actually going to cheat here and just say the ratio of AB to CD. So actually, AB is going to be twice the length of CD. Or I think it's one of the ways around, I can't quite remember, but it ends up being one of those vectors is twice as long as the other. And what this means is we have two parallel sides that are unequal in length, which means that this is a trapezium. So hopefully that helps.